April 19, 1943. The Black Pit, mid-Atlantic. The sea was a churning expanse of black ink, thick with freezing fog. Kapitän-Leutnant Heinrich Kleist, commander of U-175, felt the familiar, arrogant confidence that only came with the deep night. The U-boat was surfaced, charging batteries and receiving encrypted radio orders from Admiral Dönitz. Above them, the Canadian and British convoy escorts were blind. The only Allied aircraft that dared fly this far could only use bulky radar sets operating on long-wave frequencies. Kleist's own detection gear, the FuMB-9 Mucke, would sound a dull alarm if any enemy radar sweep came close. But tonight, the Mucke was silent. The night was the U-boat's sanctuary. The darkness was the German Admiral Karl Dönitz's greatest, most powerful ally. Yet, in the past few weeks, Kleist's confidence had been fractured by an epidemic of unexplained disaster. U-boats, fully crewed, fully armed, and operating under ideal conditions, were simply vanishing. They were not sinking after a protracted depth charge attack. They were disappearing in an instant, sometimes in the middle of a radio transmission. The crews whispered of ghost attacks and an invisible doom that defied every known law of naval warfare. Dönitz himself, the master of the Rudel tactic or Wolfpack strategy, was reporting catastrophic, unexplainable losses. The U-boat command, the BDU, was facing a crisis of morale, unable to explain why their invisible killers were suddenly the ones being hunted by phantoms. What Kleist and the entire Kriegsmarine did not know was that thousands of miles away, in a secret laboratory in Birmingham, England, and in the factories of the United States, a technological revolution had occurred. An invention so small, so powerful, and so secret that it would single-handedly destroy the U-boat fleet's strategic edge and turn the vast, dark Atlantic into a meticulously illuminated death trap. This is the story of the Cavity Magnetron, a simple copper device about the size of a fist that produced microwaves of such power that it allowed Allied aircraft to see U-boats in total darkness. The German admirals laughed at the idea of aerial radar hunting until they finally examined the captured technology and realized, with a chill of dread, that they were not just a few months behind the Allies, but a full decade behind in fundamental radar physics. This is the moment when the unseen war was lost, and the U-boat threat, the single most terrifying weapon of the Axis at sea, was rendered obsolete in a matter of weeks. The crisis that drove the invention of the magnetron was the devastating effectiveness of the Wolfpacks. In late 1942, the Battle of the Atlantic was reaching its bloody climax. U-boats were sinking Allied merchant shipping faster than the Americans and British could replace them. The primary U-boat strategy relied on two things: speed and stealth under the cover of darkness. They could only effectively attack convoys at night while surfaced to reload torpedoes and charge batteries. Admiral Dönitz, the architect of U-boat dominance, had leveraged Germany's early successes into a near stranglehold on Britain. Winston Churchill himself would later admit that the only thing that truly kept him awake at night was the U-boat threat. The losses were astronomical, measured in millions of tons of steel and vital supplies. The Atlantic was a dark, lawless graveyard where the U-boat was the undisputed apex predator. Dönitz believed the vastness of the ocean and the inherent limitations of Allied technology were his permanent, strategic allies. German military intelligence had meticulously documented the limitations of Allied radar, providing a sense of technological complacency that would prove fatal. The Allies fought back with radar, but early models, like the standard ASV Mark II, used long radio waves, meter wavelengths, around 1.5 meters. This frequency required large, unwieldy antennas on the wings of aircraft, making the radar inefficient and highly detectable by the U-boat's own warning receivers. The German Metox receiver could detect the incoming long-wave radar from so far away, sometimes 150 miles, that the U-boat had ample time to dive and escape. This technological advantage, combined with Dönitz's brilliant coordination, created the Black Pit, a vast area in the mid-Atlantic where Allied air cover was ineffective and U-boats reigned supreme. The Metox receiver was the Germans' digital guardian angel, confirming their technological superiority in counter-detection. The entire Allied war effort, the flow of food, fuel, and weapons across the ocean to Europe, was on the brink of collapse because the Germans were winning the electronic war of detection. A technological breakthrough was not just desired, it was a matter of survival. The Allied scientists were under immense pressure to find a power source that could generate far shorter, higher-frequency waves that were both more precise and, crucially, undetectable by the arrogance of German counter-technology. The goal was to jump from the meter band to the centimeter band, a feat the German scientists had declared technically impossible for airborne, high-power application. They were locked into their belief that powerful, high-frequency energy generation was only possible through massive, inefficient devices. This intellectual arrogance sealed the fate of the U-boat fleet long before the first magnetron was mounted in a bomber. The long-wave radar was visible, noisy, and inefficient. The U-boat captains felt superior, knowing their Metox would scream a warning, giving them 30 minutes to disappear into the depths. This confidence bred an operational lethargy. Why fear a blind enemy? This overconfidence would prove to be the most fatal flaw in the Kriegsmarine strategy. That breakthrough came from two physicists in Birmingham, England, in 1940. They invented the Cavity Magnetron. The device was deceptively simple, a copper block with cylindrical holes, cavities, that when excited by a powerful magnetic field, generated intense pulses of electromagnetic energy, microwaves, at the centimeter wavelength. Specifically, it operated at 10 centimeters, which was a technological chasm away from the 150 centimeter waves that the Germans were monitoring. The internal physics were elegant. The copper cavities acted as miniature resonant circuits, forcing the electrons into a swirling, high-energy dance under the magnetic field, focusing their energy into a tight, incredibly powerful beam. This breakthrough fundamentally changed the relationship between power and size in radar technology, a revolution that Germany was completely unaware of. The British government immediately understood the strategic value of the device. It was too important to keep solely within the besieged island. In the desperate summer of 1940, a top-secret delegation, known as the Tizard mission, traveled to the United States. The mission was led by Sir Henry Tizard, and the cargo was the magnetron, perhaps the most valuable piece of technology ever transferred in history. It was delivered to the Americans, effectively giving the United States a 3-year lead in microwave technology before they even fully entered the war. This unprecedented act of scientific cooperation between the Allies fundamentally ensured the victory in the Battle of the Atlantic.
The difference was revolutionary, representing a jump in radar technology comparable to going from a simple radio receiver to a high-definition television. Microwaves were incredibly powerful, yet required an antenna only a few inches long, allowing the radar set to be miniaturized and installed easily on small, nimble aircraft like the Vickers Wellington or the specialized B-24 Liberator. The smaller antenna meant it could be concealed beneath a fairing, making the radar almost invisible to visual detection, compounding the U-boat's vulnerability. Crucially, centimeter waves were short enough that they could detect tiny objects, like a surfaced U-boat, a periscope, or even the small wake a sub left on the water. The older long-wave radar was prone to interference from waves and weather.
The copper module lay on the bench like an ordinary relic, a piece of hardware stripped of paint and mystery. Yet when the Berlin technicians lifted it under the cold light of their laboratory, they felt a small, intimate terror, not the kind that announces itself with thunder, but the kind that arrives as a single, irreversible understanding. This was the instrument that had turned night into daylight. This was the quiet engine behind the deaths of men who had trusted the sea as shield. In the hands of the enemy, it had become a detector of ghosts. The magnetron, a few centimeters of copper and cavities, carved with a precision that said more about minds than about machines. For the Allies, it had been a technical triumph wrapped in operational secrecy. For the Kriegsmarine, it was a revelation that tore the seam between doctrine and reality. The device's presence in German hands was not merely evidence of enemy capability, it was a verdict. Dönitz recorded his bafflement with a precision that was almost surgical. He noted numbers, loss rates, coordinates, all clinical, all trying to translate grief into data. Yet within the columns of figures was a deeper confession. The Admiral was reading the language of defeat. The routines that had once worked, Wolfpacks that drew convoys into ambush, night approaches that relied upon darkness and silence, were now obsolete in a single stroke. The ocean had lost its darkness. The air above it had become an informer. Operationally, the effect was immediate. In the open ocean, U-boats no longer had the faint comfort of uncertainty on their side. The Mark III's centimeter waves reflected off conning towers, periscopes, and hulls with a clarity the Germans had not believed possible. Aircraft could locate a submarine at night as if it were a ship in daylight. Escort planes that once stumbled blindly across convoys now swept the sea with surgical intent. Each detection produced an unavoidable sequence: sighting, attack, explosion, silence. The human cost sits in the margins of the reports, in the terse telegrams that arrived at command. U-boat missing, presumed sunk. Each sentence represented a crew, a set of faces, a community swallowed by the long Atlantic night. With each loss, morale eroded, the psychology of survival shifted. Where once crews embraced the Wolfpack ethos, the philosophy of domination and hunger, they increasingly carried a nameless, superstitious dread, an invisible hunter that struck without pattern, an omnipresent eye that could pierce their most guarded moments. Engineers in Germany rallied, laboratories were swarmed. Telefunken and Siemens, the old pillars of German radio and electronics, convened teams and tore through their own theories with a kind of shame-driven desperation. The magnetron's cavity resonator, its cylindrical hollows and tuned geometry, revealed a design ethic that prioritized simplicity, resonance, and the exploitation of microwave behavior in a way German models had not. The Germans had concentrated on large power tubes and cooling systems, klystrons and magnetrons of a different philosophy, assuming that smaller wavelengths required prohibitive engineering. The captured device forced them to confront a brutal truth: they had been solving the wrong problem. The tactical consequences followed in waves. Dönitz and his staff sought countermeasures that were simultaneously practical and symbolic acts of defiance. They ordered additional anti-aircraft guns on deck, awkward arrays that made a submarine look less like a predator and more like a floating battery. The transformation was grotesque. The submarine's stealth had always depended on disparity: speed under the water, silence on the surface. Loading guns and crews for a surface fight was an admission that the undersea predator could no longer hide. It changed the submarine into a hybrid of offenses that made little sense tactically: slower submerged speeds, noisier approaches, and a steel hull that called attention with every radar reflection. Other ideas were no less desperate. There were experiments in radar-absorbent paints, in makeshift plasmas and screens to damp reflections, in paint and material adjustments that theoretically scatter and soften microwave signatures. There were attempts at strict operational alterations: move only by night while submerged, a slow, fuel-inefficient tortoise-like progression, or transit in escorted flotillas under the temporary protection of surface ships and aircraft. These were not victories in design, they were compromises of survival. If a war of movement had once given advantages to a bold submarine commander, the new reality favored endurance and attrition, conditions the Kriegsmarine was ill-suited to accept. On the human level, the submarine crews were the ones who felt the new reality most directly. A U-boat is a small world compressed to a steel cylinder. The smell of oil, the rhythm of diesel engines, the subtle choreography of men who have learned to live by schedule and by silence. When that order is disrupted by an unseen technological predator, the fabric of life itself unravels. Letters from former sailors show small details of the breakdown: the cigarette that is no longer shared, the patrol song that stops before the chorus, the way eyes glance upward at cloud cover with a superstitious anxiety. Boats that survived attacks came back with crews hollowed out, men who had seen the sea's newfound hostility and now carried a private awe of the technologies that made such horror possible. The numbers, once converted into statistics for planning and broadcast, had a live human face when read aloud. 43 boats lost in May, dozens more damaged, entire flotillas effectively neutralized. These figures were not merely inconvenient, they were unsustainable. Dönitz had previously used a 10% loss rate threshold in his calculations. Within weeks, that calculus was meaningless. The attrition was geometric and terminal. Germany could not replace men and machines at the rate required to sustain a viable wild ocean offensive. Fuel, steel, technicians, and experienced crews were all limited resources in a war that had become total. The dramatic pivot in the Atlantic had consequences beyond the immediate theater. Supply convoys began arriving with heavier, more consistent loads. The logistical scaffolding for the Allied invasion of Europe grew ever sturdier, its components arriving piece by piece. Trucks, tanks, and troops crossed the ocean in numbers that had seemed improbable months before. The strategic center of gravity shifted. If maritime interdiction was once Germany's most promising path to choke the Allied war effort, that option now lay blocked by a technology the Germans could neither quickly replicate nor robustly counter.
For the Allied side, the magnetron's success was not purely an artifact of physics. It was also a story of organizational synthesis, the effective translation of laboratory physics into operational doctrine, combined with training and tactics that exploited the instrument's advantages. Airmen and radar operators were trained to interpret the instrument's outputs, to vector attacks precisely, and to coordinate aircraft and surface escorts in a theater as vast as the North Atlantic. The technology's effectiveness was magnified by doctrine and logistics. The magnetron turned into a force multiplier because people learned to use it well. And still, there were human tragedies even in victory. Allied aircrews endured terrible risks. Aircraft flying low over stormy seas faced anti-aircraft fire from U-boats, unpredictable weather, and the constant threat of being shot down far from rescue. The innovations that saved convoys also demanded sacrifice: longer sorties, hazardous patrols, and the knowledge that the sea below might yield wreckage and men in need. The war's immensity made every technical gain a ledger accounted for in human costs. Back in Berlin, the surrender of confidence was audible in the way conversations proceeded. There were attempts at intellectual recovery. Projects like the Naxos receiver emerged, intended to detect the very centimeter waves that had been their undoing. But these devices were partial, insufficient in both sensitivity and reliability. They represented a reactive, not proactive orientation. The magnetron had arrived at a junction that Germany's industrial and scientific system could not navigate fast enough. It was a systemic problem, not broken parts, but misplaced priorities and a failure to pursue an alternative line of basic research that might have led to a different outcome. The reality of 1943 was that science had become strategy. The Atlantic was no longer merely a geography, it was a battlefield shaped by wave physics and industry. The Allies had harnessed their manufacturing might, their research institutions, and the quiet discipline of wartime urgency to deliver a tool that transformed naval warfare. The Germans, for all their technical pride, had allowed their assumptions to calcify. That arrogance, the quiet confidence that certain avenues of inquiry were impractical proved fatal. There is an intimate cruelty to the magnetron story. Its triumph is both small and enormous, a compact arrangement of cavities and magnetics that redefined the physics of detection. It was a microcosm of modern warfare's paradox. The same ingenuity that could save a merchant convoy could also, in a different context, produce instruments of terrifying destruction. For the men in grey uniforms and for those in ragged boots, the line between innovation and annihilation was a single discovery. In the aftermath, historians would argue about causality, about whether the magnetron alone decided the campaign. Those debates matter. They serve to clarify how agencies, institutions, and choices interact in history. But for the men who watched friends and colleagues flung into black water, the truth was experiential. A small metal tube had made the difference between life and death. When the sea that had been their sanctuary became a transparent grid, there was nowhere left to hide. The tactical changes that followed the magnetron's emergence shaped the final form of the U-boat war. Submarines operated more cautiously, limiting surface time and depending more on snorkels and shallow dives. Routes were recharted. The emphasis shifted from hunting to survival. The Wolfpacks swagger, once a psychological engine of German naval doctrine, was reduced to an occasional maneuver performed under heavy risk. The brave, even reckless attacks on convoys became rarer as commanders grappled with a chilling arithmetic. Engagement carried an exponentially higher probability of loss. This strategic contraction had operational implications beyond U-boats. Resources were reallocated, priorities shifted to defensive tasks and the protection of merchant shipping wherever possible. The theater's tempo slowed under constant pressure. The war's narrative, once full of sudden dramatic raids and decisive moments at sea, now contained a steady, grinding attrition in which Allied material throughput steadily outpaced German interdiction. The magnetron did not merely win battles, it altered confidence. Commanders who once assumed advantage now acted with caution. Men who had once celebrated audacity learned to live with constraint. That cultural change, born of technology, accelerated the collapse of an operational posture predicated on aggression and stealth. The spirit of the Wolfpack, atrophied by sudden exposure to an invisible adversary, faded into a memory as the Atlantic's currents carried away the last of the old order. And yet the story does not end in clean triumph. Technological advantages are never absolute. They are temporal strengths that require maintenance and adaptation. The Allies would themselves confront new challenges in later phases of the war. But in the spring and summer of 1943, the magnetron's moment was decisive. It was a turning point where the contours of victory and defeat were redrawn, not by a fleet's movement or a city's fall, but by the invisible geometry of electromagnetic waves. The magnetron's legacy extends beyond the wartime ledger. The same machinery that read the sea's reflection would later warm a bread roll in a laboratory, spark the invention of domestic microwaves, and become a quiet, banal miracle in peacetime kitchens. The juxtaposition is jarring. What protected convoys and defeated U-boats also, in the hands of a factory engineer who found his chocolate bar melted, gave birth to an appliance that shaped domestic life for generations. War's grotesque creativity sometimes yields everyday convenience. History, in its strange economy, stores salvation and contradictions side by side. In the end, the image that remains is oddly simple. A small copper block, its cavities humming with an invisible frequency, sitting under a harsh light as men in different uniforms looked at it and understood the scale of the damage. The magnetron did not glitter with glory. Its power was quiet, exact, and finally decisive. It delivered an answer to questions that had haunted the Kriegsmarine, and in doing so, it affirmed a larger truth. In modern war, knowledge and production can be more lethal than numbers alone. Those who study the Battle of the Atlantic talk of convoys, escorts, and tactics, but perhaps the clearest lesson is epistemological. The side that best understands and exploits the unseen, waves, codes, and circuits, will often find itself the master of visible outcomes. In 1943, the Allies harnessed an understanding of microwaves and coupled it with manufacturing and doctrine. The German admirals, confronted with a small, anonymous piece of technology, learned late what it meant to lose both the night and the initiative. Their U-boats did not vanish because of fate. They vanished because another power had learned to map the invisible. When the reports finally stopped coming in with regularity, when entire flotillas ceased to transmit, and when the Atlantic resumed its slow, indifferent rhythm, the cost was counted. People spoke then in numbers and in names, losses tallied in telegrams, lives remembered in brief notations on paper and in the private trauma left behind. The magnetron was a machine, but its consequences were human. So the story folds back on itself. The same ingenuity that brings victory on a maritime battlefield can later melt a candy bar and change how people live. Innovation, when wielded without ethical limits, can destroy quickly. When redirected, it can create ordinary comforts. This doubling is the central paradox of technology in war. In 1943, a copper cavity carved in England made the difference between the survival of a nation and the collapse of a submarine armada. It rewired the Atlantic and rewired history. And now, as we look back across 80 decades, the magnetron's cavity sits at an intersection of memory and meaning. It is a small, consequential shape that teaches a vast lesson: humility before physics, respect for innovation, and the understanding that in modern conflict, the invisible often decides the visible. The German admirals learned this truth bitterly when they examined the captured set. The cost of that lesson was measured not in diagrams or schematics, but in deep water and silence, in the final terrible muteness of sons, husbands, and comrades who never returned to tell the tale.